Hello, this is Kutay YILMAZCOBAN. I'm here for Finite Element Method for Engineering Applications lecture. So I will try to explain some initiatives and syllabus of the class first, and we will continue with the simple definitions, fundamentals of what the finite element method is, and mathematical background sometimes, and applications that we are going to do.
Let me explain what we are going to do in this term. As you know, finite element method is a kind of method. With the help of mathematics, we are going to develop some type of engineering solvers. Finite element method, it's not a code. It is a kind of mathematical way to create an engineering solutions. And we need to know initially what we have, what is the problem. I am a mechanical engineer, but an engineer cannot be a mechanical, maybe electrical, maybe environmental, maybe structural. It's not important. The basics way we are dealing with is the same. If we try to approach the problem, to solve the problem by using classical analytical engineering solution techniques. For example, we can talk about the engineering mechanics or solid mechanics, mechanics of materials, or continuum mechanics. These are the basics of engineering structures. So as I am an engineering mechanics faculty, I want to continue with generally solid mechanics problems, but we will give continuum mechanics including fluid dynamics, or sometimes electrical solution techniques, magnetisms, and etc., etc. But I know that most of you are coming from the mechanical engineering basis, so you are going to deal with the basic of mechanical engineering solution technique, that is starting with solid mechanics. And you know that solid mechanics is a part of elasticity theory, or we can say theory of elasticity, continue with theory of elasticity, but generally we are not lecturing plasticity techniques in the undergraduate students, for the undergraduate students. So initially I have to talk about the rate for the joining of the classroom. For this term, you have to join to the classes. I'm talking about live, minimum 35% after the class was finished. So you have to join 70% of the classes, unless you will fail from the class, and it doesn't mean anything to you. So you have to listen live, and it is much better, especially for the graduate students like you, are going to explain the theory background in this class. So you need to know the basic assumptions of the mathematics first. I'm talking about the calculus definitions, trigonometry maybe sometimes, and maybe not maybe, it is exactly the linear algebra matrix equations. So if you are a capable guy after finishing the finite element method class, you will try to develop your own software with the help of mathematical techniques which I have given to you. So this means that we are going to give some different techniques for the solution of engineering applications, and you are going to take that mathematical background and apply to the problem what you are dealing with, what you are focused, and you will create a solution regularly. You are making those solutions in the regular mechanical engineering classes like strength of materials or fluid dynamics, etc., etc. You have a problem, for example, bending problem, torsion problem, extension problem, compression problem. You will take the problem and you need to solve for what? Sometimes stresses, normal stress, shear stress, sometimes strains, and sometimes the deformations, bending deformation, extending deformation, or caused from tensile stress, or compression stress, the forces, etc., etc. And the combined loadings, combined stresses, like von Mises or Tresca. So we accept that you all know what I am talking about. You have to know the details, especially which depends on the solid mechanics. Hooke's law, Young modulus, and the directions of x, y, z, and which is causing the regular normal stresses, and the xy, yz, zx, I'm talking about the shear, the surfaces, shear surfaces, or something like that. Now I'm just talking about general information about the finite element method background. So it means we have to know initially the basics, mathematics, needed mathematics, calculus, differential equations, and as I said, linear algebra, transformations of the matrices, etc., etc. And we are going to take the problem to the engineering area, and we need to solve for what we need in the future for a problem. Let me explain the initial basics of what we need to talk. For example, we can say that maybe I should give some type of example books that you need to learn and you need to look for it. I will give some names to you. For example, we have got a few very important names for finite element methods, for structures, solids, or the fluids. Sometimes they are coming from the same basics. Every time coming from the same basic, but we are going to use it for different areas. So in the future, it's going to be differentiated. Let me explain it to you before giving the important books. For example, we have got a surface, a tabletop. We have got something on it. In classical solid mechanics, we have got a weight. And there is another thing. Tell me, what is that? Response, reaction force. This is the statics. And if you write the equilibrium of the force, Fy is equal to 0, which means reaction force minus weight is equal to 0. This is the basic. But this solution technique is not going to help me for the stresses, strains, etc. because of the statical approximation. You need to know engineering mechanics. Is this weight going to create something on the tabletop? It's going to deform it or not? If I add something, another force, we will have a friction force. And we will have a constant of friction. For example, 0.1. If this is dynamic, static version of friction force may be 0.2. So, if the force, let me say F1, if F1 is bigger than friction force, what's going to happen? We all know that this material starts to move, right? It's going to move. So the name of the class is changed now. Now it's again engineering mechanics, but not statics. It's become dynamics. But again, in the statics and dynamics, we call these type of mechanical problems that rigid mechanics. So our structure is not going to deform. just protects its shape. It means that for the engineering mechanics, statics, or dynamics, your shape, the material shape, does not gonna change. So you are not able to get the stresses, strains, etc. So let me change the problem. Again, there's a table, but I'm trying to explain it like a game. You can remember from the mechanics or solid mechanics. Which one? This is a classical bending problem. L over 2, L over 2. The total length is L. And we have got a force of F. So we will get F over 2, F over 2 here, which means we solve for statics now. And then we are going to continue with what? With deformation. Bending deformation. When the bending occurs, you can understand that there is a displacement on the top surface and again bottom surface. All of the surface change its form and deform like this, creating the delta deformation. So we will have a solution technique for that. What is that? You need to solve for second order differential equation, and you will use integration method or singularity method, etc., etc. Maybe the area method to calculate the moments from the shear force diagrams. So maybe I can say to you that we will cut this beam like this. We will have a force F over 2. Now, for the broken zone, we will have internal vertical force V. Because we don't have any X force, so we won't have any reaction force here. So I'm thinking that. But what we have next, tell me. We will add something to the V. What is that? There is no answer, tell me. It is moment, right? We have moment, shear force. V is shear force already. So when you cut the beam, you will have reaction forces and the moment. So let me write the equation. I am breaking this zone from the beginning to the cut area we called X. We called X. So if you write equation, or you don't need to write in total, let me write F over 2 plus this is plus, minus vertical force should be equal to 0. This is our shear force equation. And because there is nothing changed from the beginning till to the F force of the middle zone, the force F over 2 continues without any changing till to F. And F will come to the system, cut to the bottom. It will be now 0, and then it continues to cut F over 2 again. So we will have F over 2. This is the shear force diagram. And when you look at the bending moment, I'm going to explain it. We will have something like that. How? Because of the equations. Now, if you integrate the force equation, you will get the moment equation. This is the first way, which means when you calculate the area below this, you will get the top or the end part of the moment value. This is the area method, the second one. What is next? If you look at the figure here, you can take the moment of the system. So that is going to be the third one. And because the x, y, z directions, x, y, z, if you remember, the moment direction, it is counterclockwise, you remember. Counterclockwise for the right hand method. All of my fingers, when you rotating like the moment, index finger, the other finger, and the tiny finger. We have got 4 fingers and 1 thumb. This is hand, you know. These are explaining the moment. And this one explains the moment vector. Which means when you accept counterclockwise moment, your thumb will be the same direction with Z here. Z here is positive. So your thumb here is positive. They are the same way. Because of that, counterclockwise moment system will be accepted as positive. I think you understand, because the thumb, right hand thumb, will be the same with the Z positive direction. And this is the basic statics and vector mechanics. So I can say that this M should be positive. Let me take it M. I'm going to take the moment to the here. So we will have F over 2 multiplied by X, but the direction like this. So it is the opposite of M. We will use minus F over 2 multiplied by X. And we have got nothing because vertical force passing through the moment zone. So we have got no distance for it. Because of that, we will have this moment equation. And if you look at this equation, when you hold the V like this and put the F over 2 to the other part, you will have V is equal to F over 2. And this is a constant number. You have got no other things, just a constant scalar number. For example, if force is 100 newtons, you have got 50 newton of V force, vertical force. So it's a constant number. But in the moment, when you look at it, it is taking x. So your equation is changing. And you have to, again, take the F over 2x to the other side. So we will have m is equal to F over 2x, which is positive. You have to look at this equation. Here it is negative, but here positive. And the equation here is constant. This one is not constant, x. You can change it, which means your line is going to incline positive. It's a linear line, and again, because of here is positive, you can remember from the polynomials. Polynomial which is taking x starting from 0. If you put 1 multiplied by f over 2. If you put 2, if you put 3, and etc., etc. So this is the basic breaking zone of the beam, and we are created the shear force equilibrium and bending moment equilibrium. We will use these equations, if you remember, for the shear forces, which we can say that tau is equal to V Q over IT, or the normal stress. This is XY, and normal stress. Tell me the direction of the normal stress. Tell me. I'm ready. Look at here, X, Y, Z directions, and I am asking you, what is the direction? You can say X, Y, Z, which one? Of the normal stress. Tell me. X-axis. It's right, because when your beam faced with F force, then you push it from here, which means the top surface here will come closer, right? And the bottom will go further. So you will have the definition of like this. If I'm going to make it bigger, oops. This is 0. There's a compression. And for the neutral axis, it is 0. And then, because it's now in tensile zone, this is positive. It is coming towards to 0. It's going out from the 0. This is tensile, this is compression. And look at the direction. All of the directions are in x. There is no, or there is nothing in y direction. So we can say that for the bending like this, it is going to create a normal stress at the x direction. So bending moment, and there is minus in the beginning. And the height of the cross-section and the cross-sectional moment of inertia. And this is again cross-sectional moment of inertia. And what is the directions for the cross-section, tell me? I will view this one as the cross-section of the beam. We will have neutral axis and we can say that this is y. And let me draw a perspective view. So here is z, and here x. Tell me, which surface is belong to cross-sectional surface, bending moment of inertia? These are the simplest solid mechanics approximation you have to remember. This one should be what? It should be ZZ or Z, because you are going to calculate the cross-sectional moment of inertia considering the Z direction. For example, this one is B. Height is H. I will calculate it as B multiplied by cubic function of H over 12. So you can say that IZ is equal to B H cubic over 12. So let me continue with the continuum mechanics. If this is the basics of solid mechanics, I'm just remembering what we have done before during the solid mechanics classes. So this is for bending. You have to look for torsion, you have to look for compression, tensile, everything, or combined loadings, all of them together, etc., etc. So let me continue with the continuum mechanics. As I said, there is a beam around here. I started from 0 and continue till to the L. Before 0, And after L, we have got no consideration. We are just looking for inside of the beam. Here, 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 here. It means endless solid here. So it is continuous between the 0 and L. So our beam continues in here. So we can say that up to this belief, this is solid mechanics, but we can say that it is continuum mechanics. For the fluid flow, let me draw you a pipe like this. We have a pipe. Or I can change the initial and end point of it. Let me draw you a regular pipe. It is an inner diameter and outer diameter. So I am sending a kind of fluid. It can be water, oil, whatever it is. I don't care. I am sending the fluid or gas inside of the pipe, and I need to calculate the equation. Before the zero zone, like in solid mechanics here, there is nothing. I don't think about it. I'm starting from the 0 till to the x or L when x is equal to L. So I can draw the same limitations. 0, x, and L. I can say that between the 0 and L, the liquid or gas inside the pipe explains the continuum mechanics again. So we have got the same ideology. In solid mechanics, we have got a solid which continues from the beginning till to the end. In the fluid dynamics, again, we have got the same. Starting from the inlet till to the outlet of the liquid. I'm not talking about the pipe. I'm talking about the liquid which is inside here. And it's not a turbulent flow. It's a natural flow. So the pipe is filled with all liquid. There is no air gaps, etc. So again, I am able to tell that that is continuum mechanics. This is the basic connection point of the solid and fluid dynamics. And we are using the same approximation for finite element method also. We are using engineering elasticity initially and continuum mechanics for the constitutive equations, which means you have to know the problem initially. You have got a bending problem. You need to solve for deformation, bending deformation. You have to know the solid mechanics first. You have to know what the force is, what the moment is. You need to know what is the way you will use the true integration method or area method or singularity or something. This is the constitutive application. You have to know the engineering background, and then we will solve with the help of finite element technique. What is that? A different mathematical approach. If you accept this whole solid material here as a one element, the solution of analytical approximation and finite element technique will be the same equation. A different mentality maybe, but the equation result will be the same. You are using the same equation, but when you increase the number of elements, which now we are starting to develop the finite element. This is the element. I'm going to divide it like this. Divide it more. Divide it into 4 now. It was 2 and now 4. Why are we creating these type of discretizations? Why I am dividing the element more? To get more precise results. Here, if you need to get more precise results, you need to divide the structure more elements, with more elements. So this is finite element method. Initially, we have got a CAD model or structure. You will divide it or discretize it into some more little elements. We call mesh to them. Mesh, you know, net. For example, fish net, volleyball net, if you understand. So you will discretize it, some more little elements, and you will get much more precise results. But there is a kind of optimization needed for the mesh regime. This doesn't mean you will divide into the eternal elements, so you will get the perfect results. Of course it is, but you are not able to divide it into the eternity. You will have a kind of constant number for the division, or your computer capability is not enough to calculate the eternity. So, for example, you will divide it into 4, you will divide it into 10, you will divide it into 100,000, 2 million, but maybe you are not able to calculate the 400 million elements, etc. You will pay more to get much more complicated workstation for that type of analysis. But there is a kind of limitation for that workstation also. Much more elements, much more source. Because of that, we need optimization. What is that? If you try to solve the problem, for example, let me change here. we try to solve for extension problem. I hold it with probably two ends. I am applying F. We have a cross section, circular cross section, and we have got the area A. So I need to calculate the deformation, if you remember, delta L. And let me give the length of the bar L. Delta L is equal to FL over AE, Young modulus. The material property is not included. This is a kind of material model for a bar when it is applied by a force in tensile behavior. So you need to solve for in theory of elasticity, not a plastic region. So for this equation, because of there is no plasticity parameters or unknowns, when you put the force too much, you won't get a correct answer, which means I have got a cross section of 1 centimeter and the length is 100 centimeters. But the force is 1 kilonewton. What is the meaning of 1 kilonewton? It is 1000 newtons. And when you try to understand the value, you need to erase 1 zero maybe. We can say that it is close to 100 kilograms. Approximately. We can say that 100 kilogram, 1 centimeter, 1 meter, maybe that's okay. But if I increase it to 1 kilonewton to 500 kilonewton, $500,000 Newton, which is a huge load for this type of bar. So you have to know that in the engineering perspective, you have to know that this bar will be demolished by a huge force like 500 kilonewtons. So if I am writing a finite element code, and I know here, you can use this equation. This is a material model for a bar in 2D or 3D. It's not important. You have to know the area, force, length, and Young modulus. You will calculate the deformation. But because the force value is so high, this is modulus of elasticity. You won't get the correct result of delta L. Maybe the bar will come here, like in the tensile test, and it's going to demolish it. But for the computer, using with this equation, maybe you will get the result for delta L, maybe 10,000 centimeters, for example. The computer will calculate it. It does not have any idea what is going to be. That idea should be inside of your brain. You have to know it. You have to know what is going on. Is it a elasticity problem or plasticity problem? When it is plasticity problem, you have to add yield, you have to add fractures, you have to add many more things, many more parameters. So this result won't occur. Maybe you will see maximum, let me say, maybe we will see 120 centimeters maximum. After that, it's gonna demolish and broken down. So when you are giving this to the computer, let me tell you, we have got a graph. It is stress strain graph, you know. And if you give just the Young modulus, computer will understand that there is a line, elastic line, starting from 0, continuous to the eternity. So whatever you have given to the system, computer will calculate it, but you will get the wrong results maybe. So you have to understand, you have to know what is the breaking point, what is the yield stress, etc., etc. So this is a basic material model for elasticity. But if you know that the force is too high, you won't use this graph. Maybe you will change it like this. The original graph here. But we will try to approximate like this. Here is the first module, which is theta, which is giving the E, Hooke-Stall and Young modulus. What is that? Sigma over epsilon. But here, there is another modulus. Maybe we can say theta 1 or alpha beta, it's not important. This is called tangent modulus, E tan. So, and this model now, initially it is a linear model, just one line. Now, we have got two linear zones, one linear zone, and this is the second linear zone. So this type of material models, we can say that it is a bilinear model. First linear, second linear. It is a bilinear model. It is maybe bilinear kinematics or different things, not just kinematics. Bilinear plasticity models can be, or we try to approximate the real graph, so you can increase the number of this line, for example, first, second, third, fourth, etc., etc. You have got one more theta for every angle. So there are many modules. This is multi-elasticity models. This one seems it is more closer to the original graph. This one is a little bit far away, but you have to measure correctly. So if you have got a good ability to measure the details, you can use this one. If you don't, maybe you can use this one. But after yield, it's not going to give so much difference. Maybe some type of behaviors can be changed. But again, for the end of the line, you have to say that this is a breaking point, unless again here it is continue to eternity again. You have to say that here is breaking point, point of failure, failure parameter, error parameter to the computer, and the computer will understand when your stresses or strains come closer to this value. The results can be seen in the finite element screen closely to the real deformation. And is there any question up to now? If you don't, I'm going to continue. I think there is nothing. So, for the finite element techniques, we have got many different issues. If you understand here, for example, one element, or we can increase the number of elements. Very simple, elastic and tensile deformation. The force is good enough and the system is still in the elastic region. You already know it. And then you are able to use this basic consumption and to get the results very close, or if you use a 1D line element, bar element, it will be the same with the strength of materials deformation solution. I'm trying to tell you that you have got a problem like this. If you make the problem more simpler and draw the tensile bar like this, one line starting from 0 to the 100 centimeters, and there is no cross section, but you will give to the equation a value, but for the CAD model there is nothing, there is just a line. For the strength of materials, if you say that the beam has got a cross section of square, rectangle, or whatever it is, I beam, T beam, L beam, it doesn't matter. We are using a mathematical background of one line. And to solve the one line, we are adding areas. It is a kind of skeleton, and you are adding the meat on the skeleton. So the finite element softwares are working in that mentality. Up to this perspective, in strength of materials, we are using the equations of a line, of a curve, not a solid. Because of that, when you use the beam, just a line element, and calculate it with the finite element method, the solutions will be exactly the same with the strength of material solutions. But you preferred a 2D element like this. The solution will differ. Or if you use a 3D element. The finite element method solution won't be the same with strength of material solution, because finite element tries to answer the solid behavior, or here the surface behavior, but for the solid mechanics it is using the line equation, but it is adding to the structure onto the skeleton. So what we understood from here, if you try to calculate the equations by hand analytically, in the finite element method, you have to use the line or bar for beam element for an exact comparison to the analytical method. I think you understand something. From now on, we can say that we have got a structure like this. For the finite element method, to decrease the computer usage, memory usage, or calculation, decreasing the equations. Maybe I should erase the 2D element. We should accept 3D. Let me say this one. Our problem is a 3D problem. But in a tensile stress, you already know that if you try to calculate the normal stress here, we need to know this equation, and then we will put that values to the pressure equation. Sigma is equal to F over A. For example, you know the deformation size, you knew the length, you knew the material, you measured the cross-section area, just you don't know the force. So from this equation, you calculate the force, put the force here, and you have the sigma now. For the deformation, if you know the deformation rate and the initial length, when you accept the equation delta L over L, it should be equal to epsilon. So these are basics, but instead of solid, I can make it simpler using a line element. Creating a line element, maybe I don't want to discrete the element, just one element. So discrete into two, one and second element. Discrete it into four, one, two, three, and fourth element. This is a 1D element for the finite element method. And if I am accepting the problem in 2D, let me show you the axis. X, Y, Z is something like that. So this is the surface of XY. I will develop the model into the 2D. This is an area, but this is not a good comparison because you have the volume, you have the just maximum surface of the beam here. And after that, you will have the solid model. 1D model, 2D model, and 3D model. And now for the 2D model, you can also divide it here. But in 3D model, let me draw like this, more bigger. You will able to divide here. Divide here. And also these continue here. Etc. etc. And to get a good result, we need to describe the structure. And I'm talking about the mesh. Mesh should be beautifully designed, like rectangle, square, or something like that, or a cake, part of a cake, a piece of cake like this. If it is not, the solutions will not give a good result, because under deformation, the structure has got an ability to deform the element into a defined angle. For example, here it is 90 degrees. When a huge deformation, this will come here, something like that. It's going to increase. Maybe it's going to come to 0, maybe 180. The finite element code is not going to let you to calculate the values. And because the directions one come on to the other one, it's going to give a wrong result. So there is a kind of limitation. Some of the computer codes using 20 degrees, some of them more, some of them less. Because of that, we are generally using so for the 1D element, there is no problem. All of them just one line. For the 2D element, yes, these are rectangular meshes, but instead of this, maybe the computer automatic software will discrete the system like this. Triangles. But very simple models generally is not going to result with this. Simple models generally resulting with we call sweep, fine and sweep mesh. Fine means the number of elements will be more. But sometimes you need to understand much more detail, more closer to the real result. You need to increase the number of elements. So we will say that create a refinement and find more finer meshes. If your mesh is so far away like this, this is a coarse mesh. This is a fine mesh, and maybe you will try to understand this region more. you will refine here and add more to the center. You understand? It means that meshing is very important issue when you're talking about the finite element method. If you don't mesh properly, you won't get the good results. Or maybe you will get very bad results. Our first idea, we need to create rectangular meshes. If it is in 2D rectangle, if it is in 3D, we're gonna say hexahedral elements. This is an hexahedral element. But also in 3D, there is a kind of surfaces, not a smooth area. So the computer will try to get triangular or wedge or pyramid meshes. If it is not so smooth like this. So you will get a pyramid or four-faced. 1, 2, 3, 4 hexahedral. This is the four-faced element. And it will change. Or like this. Maybe like this. It's a kind of cake. This is based and chained up to the operator. So if you change it, it is your ability to get the good results up to the equation. You have to know the equation. You have to know it's elastic or plastic. You have to know which size of the mesh is going to give a good value. So should I divide this solid into 100, into 1,000, into million? It changes, of course. And you cannot divide the system that is not capable by the computer software. So, or your computer hardware. Your computer hardware may not be enough to divide the system as you think about it. Millions of elements. It's got a central process unit, and that is got many limitations. So you have to think about it, solution time, computer abilities, the weather conditions, cooling, etc., etc. Many other disturbing parameters to your solution. And for example, when you solve for a tensile stress problem, the same loads, everything is the same. Mesh number is the same. Everything is the same, but the computers are different. So maybe you can get different results from the different computers. But I'm not talking about very simple problems. I'm talking about more complicated, used lots of elements, etc., etc. These are going to use the computer CPU so much, so it's going to heat it up, and again creating a calculation mistakes. Yes, let me continue with an approximation. If you remember tensile test, let me draw it again. This is a regular stress strain. When you testing your material under tension, you have a tensile test machine. One jaw is static, the other jaw is holding the other side of the sample and trying to taking apart, creating a tension. So you need to measure what? Initially, with the help of load capacitor or load cell, you will measure the forces, and up to its precise operations. Maybe one of the load cell gives 2 data in 1 second. The other one may give 5 data in 1 second. Maybe the other one will give 100 data in 1 second. This is one parameter. And the other one, let me say, if you gain weight, you have eaten too much. You are so fat now. So you need to measure your weight. You are going a kind of, we call in Turkish, you remember baskül, right? And you step on it and you measure your weight, you get, for example, 100 kilograms. You said, oh, I'm so fat now. But if you go to the weight measuring system of a truck, it is measuring tons of tons. When you step on it, the system is not going to move because your weight is so less, so little to change the value of weight. Up to this perspective, when you are using a load step for measuring the force, you need to know the sample. What will be the reaction force around? You can say that the values may be 400 kilonewtons or 500 kilonewtons. So you need to select a load cell between those values. You need to know the range. Or you are going to use your gold and you need to measure it. You will go to the jewelry store and get the guy measure the gold, and they are using so tiny measuring equipment. It's able to measure maybe after comma 2-3 digits. It's so precise. But when you look at my first example, the guy went to the measuring area for a truck. It is measuring huge range. So you need to know what will be the reaction force of your sample. Approximately, you have to know it. You have to buy that type of load cell. And again, you will measure the displacement, deformation. You need to have a linear transformation measuring system. And especially, we don't believe in too much to the test specimen. Because of that, we will add extensometer. Extensometer is measuring the length of just the sample very precisely. Mechanical extensometers or digital extensometers we call digital image correlation systems, or let me say laser extensometers. You have a sample like this. You just put a few dots to the system and laser recognize the dots, and when you operate it or draw a drop down sample, there are the points. When you apply the tensile test, these ones, the distance between these nodes will increase, and the distance between the transverse nodes will decrease. Laser is recognizing that data and give much more precise solution, just not for trusting the test setup measuring system. So, what is our goal? What is the initials? First, you will measure force, and you will measure deformation. The finite element technique is, again, depends on the same ideology. You can calculate the force or displacement, but initially we have to understand the displacement. So we will calculate the displacement. Up to displacement, we will find the forces, and then we will create the matrix system to solve for all of the elements, and we will find the strains, which belongs to again deformations, and then the stresses. We know the area, or the system is able to read the data, or with the help of CAM, it can understand the area of the sample. But generally, you are entering the cross-sectional area data, and up to the result of load cell, your force will be over there, the area measured, and the computer, the tensile test setup, is going to give you the stress value. So if you give the initial length of the system with the help of laser extensometer, again the computer is now able to calculate the strains. So with all of them, you are able to calculate sigma stress, epsilon strain, and now Can you hear me, guys?
Because of some connection problems, we have to finalize the lecture for today. So see you on next week. The class is over.